So today we are talking about LAN and time. Does anyone know what LAN stands for?
Looks like local apparent noon.
Oh, yep, I have it on there.
You gave too big of a clue.
Dang it. I needed to read my PowerPoint before I popped quiz you. So local apparent noon is going to be when the sun is right above us. And locally apparent for us. And then we're going to figure out how to get a LOP using local apparent noon, how to predict when the time of local apparent noon will be so that we can shoot it with our sextant to get a LOP. And then we're going to talk about Polaris and getting a quick LOP for shooting Polaris, which is the North Star. And then we're going to do a quick little couple slides on sunrise and sunset. But I will be doing the homework problems for sunrise and sunset on my tutorial video. So you'll see step by step how to do sunrise and sunset on my tutorial video. But it's just going to be a quick little intro on the PowerPoint.
Hey, a brief quick question. You said that local apparent noon is when it's right above us.
When it's at its height.
When it's at its highest. Okay, so it doesn't have to be right above us.
No, and because we are not in the tropics, meaning below and above the Tropic of Cancer and Capricorn, it is never going to be exactly above us.
Right.
Never going to cross our zenith.
Got it.
It's always going to be to the south of our zenith because we are not in the tropics. So yeah, just at its highest. Excuse me. Okay, well, let's dive into it. Okay, so here we have kind of our celestial horizon. The sun rises in the east, so it rises and gets higher, higher, and higher, and then at its highest point is local apparent noon, and then it starts setting in the west. So as you can see, the bearings are going to change pretty rapidly throughout the day, or azimuths of the sun. And then at the highest point, it's generally south because we are in the north. So it's going to be generally south of us. And that's going to be that peak high position. And then we're going to go, then it's going to set in the west. And that's why we have pretty sunsets on the west coast. So that is the definition of local apparent noon. Now, when we look at this guy over here, it's kind of the same kind of picture. The sun is following this orange dotted line. And then on the next couple slides, we're going to define what this green angle is and what the red angle is. So stand by. So that is the definition of local apparent noon. It's basically called the meridian passage of the sun. And you'll see that on here. So the sun is rising, 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 and when it crosses our meridian, that is local apparent noon. And then it starts setting and setting and setting. So you could have a meridian passage of a star, of the moon, of the sun, of a planet, of anything. When it's the sun, we call it LAN, but it's a meridian passage is just another term for it. It's when it passes ours and then starts setting again. Does that make sense? Meridian passage? Okay, so this picture shows the sun meridian passage if we're to the north of the sun. But it can also be a star, and those are called upper transit when it rises, 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 and then sets, sets, sets. The lower transit is when it's on the other side of the pole, but we can still see it. So then it would be getting lower, 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 peaks at low, and then gets high, high, high. as the sun moves. So that we also call that a backside of a star. The calculations for that are really complicated. We are definitely not going to get into that, but it's possible. It just, when we do our little calculation for LAN, it's a little bit different for the backside or a lower transit. So we're mainly focusing on the upper transit or meridian passage of a body, specifically the sun for LAN. So when we observe this happening, we use our sextant and we know ballpark of when LAN is going to happen. So we will be following our sun, keeping it on the horizon and increasing the altitude. So that would be turning it to the right. I'm increasing my altitude. And then if I'm still keeping it on the horizon, the moment where I have to turn it to the left and it starts setting, that is my LAN. So I'm going to note the time that happened. So I'm going to have my watch, note the time that it happened, and then note what altitude it was when it was at its peak. As soon as it starts setting, that's the altitude we're going to use for our HS. And then we're going to know the time for our calculation.
Bree, I thought there was you measure it when it hangs. You know what I mean? Where it doesn't go up, doesn't go down, and they use the HS at that point. Or are we splitting hairs here?
Splitting hairs there. Yes, that's correct. Right when it pauses, but you know, it's rising, pauses, and then sets. So you'll see when you're doing it, you're like, is it setting? Is it setting? Okay, it's setting. Then it was then. So you're correct. It's when it's at its peak.
Right.
But you know when it's at its peak once it starts falling again.
And then what is kind of the time frame for that sequence typically? For your, let's say your window when you would want to get that number recorded. I mean, are we talking about seconds or minutes or?
No, I would say a minute. So we're gonna have like a ballpark. It's gonna be at 12:04. So at 12:03, I might start looking at it and find it where it's stable on the horizon. I have it in my sextant and just kind of watch it for a minute as it rises. And then once you know that it's not moving and maybe it goes down, that's LAN. And if you're like, 10 seconds and a slightly different altitude than the person standing next to you, that's fine. So if you're within a minute, you're good. We'll go with that. That it's not going to be a giant difference in this whole calculation. So ballpark. Does that answer that question? Okay. Okay, so the two things that we need are that sextant altitude and the time. And this is going to be our little shortcut. So our steps to this shortcut is to, step 1, observe the altitude and the time. And then we are convert that HS to HO, which we are all experts at now, right? We have to go from the raw sextant altitude, and then we correct for dip and instrument corrections, and then also refraction of where the sun is, and that's our A1 or A2 correction. And then we also need to use the time to calculate declination. So if you remember, our declination is a pretty simple calculation. It's D, or declination, a little d, and then declination. So we don't have to do a ton of minutes and seconds or longitude, it's just a short calculation, just dec d dec. So that's a lot less intensive than the full site reduction. And then we'll use that HO and that declination that we just calculated to then calculate our latitude. And it's just little adding, subtracting for that. So that's why it's a shortcut, because we're only, part of the site reduction form we're doing is the HS to HO and then the declination. Those are the only parts of the whole site reduction. So we don't do GHA, we don't do anything in Pub 229. It's no assumed position or anything like that. It's just using HS to HO and declination. So that's why it's a shortcut. And we're going to use that latitude as an LOP. So if we calculate our latitude at whatever time it was, that is an LOP, and we could advance or retard that LOP depending on what sun fix we're going to get, or just use it as an LOP to see if our DR is close. So how do we find the latitude given our, so step 3, I put in here, use HO and declination to calculate latitude. But how do we do that? That is our next slide. We're going to add and subtract our zenith distance. Okay, let me go to this one first. So step 1 in that step 3 is to calculate your zenith distance. So if our sun, this was kind of at the beginning, how our sun goes high, 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 and then low, 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 low. The red section, so from the horizon to where the sun is, the height of the sun is the altitude. From the zenith, so that's above me, to the sun is the zenith distance. So from the horizon to the sun is the altitude. From the sun to the zenith, which is directly above me, is called zenith distance. So zenith distance equals 90, because it's at 90 degrees, right, from your horizon to your zenith, minus your HO, gives you zenith distance. Does that make sense? So now when I refer to zenith distance, it's kind of like, not the reciprocal or the complement of your HO. 90 minus that complement, I think. Anyways. Okay, so I'm gonna go back to this slide. So now when we find our zenith distance, we're gonna use these types of images that we hopefully have a ballpark of where our latitude is. Do we think we're in the northern hemisphere or the southern hemisphere? And in relation to declination, are we way north of it or way south of it, kind of thing? And this is how we decide if we add or subtract our ZD and our declination. So our ZD and our declination, we're either going to add them or subtract them to get our latitude. And how we decide if we add or subtract is, I like to actually draw this little picture out. You know, it doesn't have to be exact by any means. It's just, hey, the sun is to the north of me. I'm in a pretty low latitude. So in this case, in order to get latitude, I would subtract my ZD from my declination to get latitude. In this case, if I'm in the northern hemisphere, the sun is in the southern hemisphere, because that's what declination is. To get my latitude, I'm going to have ZD subtract my declination, and I'm left with latitude. In this one, the sun, so this one's for us right now in the summertime. The sun is to the south of us for declination. So to find latitude, which was our LOP, we're going to add zenith distance plus declination, and that will give us our latitude. So zenith distance is from the us to the sun.
So the flip side of the middle one is the same calculation, correct? If you're in the southern hemisphere, the sun is in the northern hemisphere?
Correct. Correct.
Right.
Correct. So yeah, either way, you just draw the picture, and with your zenith distance and declination, you're either going to be adding or subtracting them. So if you add them and your latitude is completely off of where you think you are, then subtract them, and you'll probably get a closer number. So I like to draw the picture so I can visualize it, but if you're really confused by the picture and you get a crazy number, do the opposite, if that makes sense. Okay. So again, our zenith distance, right from us to where from our zenith to the celestial body. So quick little review, our shortcut. We observe the altitude, HS, and note the time. Then we use that HS and we convert it to HO using our nautical almanac. And then we use the time and calculate declination. Quick little calculation. So this is the abbreviated site reduction form on step 2. And then we're going to use that HO and that declination to calculate latitude. And we use that latitude as an LOP. Any questions so far? Okay. Good, good. Okay, so quick recap on how we do HS to HO. We have our instrument error, which in most cases is always 0. So I didn't even put it on my little thing. Index error. So that's what we get before we shoot when our horizon's going to be at the same. So that's the error that we create ourselves before each site. So that's the index error. And then our dip is height of eye. And then we have our apparent altitude, our HA. And then we can calculate or look up in our little bookmark, our refraction correction, our A2. And if we want, we could even do the A4, but we'll just do A2. And then we get our HO. So then we'd have to do 90 minus HO to get zenith distance. So we still have to do that part of the site reduction form. To calculate declination, we have declination, little d, declination. So we do have to look up the page in the daily page in the Nautical Almanac, get our declination, and then go to the minutes and seconds and get our D correction. So we still have to do that step. Then we're going to use our little drawing to decide if we're adding or subtracting. And then we get LAN. So the next step is, when is LAN? So how do I know this is going to happen? Or am I just going to stand out there for an hour waiting for the sun to peak on the horizon? It's in the Nautical Almanac. So it is under sun, and it's meridian passage of the sun. So that's when the sun is going to pass your meridian at a given day. So the example here they have for the 29th, 30th, and 31st of July, it happens each day at 12:06. So that's the meridian passage at each of these days. So now we're going to talk about the concept of time and when this is happening. So where are we? This meridian passage that they're talking about here is going to happen on the central, the time zone's central meridian. So whatever time zone we are using, this 1206 is going to happen on the center of the time zone, or the central meridian. And if we remember our zone description table, it has which meridian is used for each time zone. Or we can just multiply the time zone by 15, and that's the central meridian. So that's what I do because it's easier than looking it up. You just multiply the zone description by 15, and that's the central meridian. Now, where are we in relation to that central meridian? Are we to the east or west? So will the meridian passage happen at the central meridian before or after it passes us? Are we to the east or west of it? So let's look at that in a picture form, because you know me and my little drawings here. Okay, so this is our short picture of our time zones. So every time zone is 15 degrees. So 0 is the central meridian, or the prime meridian, but it's the central meridian for the zone description 0. For 1 degree west, it's 15, 30, 45. So every 15 degrees is a central meridian for the time zone. Now, technically, the time zone goes 7.5 degrees one way and 7.5 degrees the other. So it's the central meridian of the whole zone description, or time zone, if you will. So if the sun is passing the prime meridian at LAN, right on top of it, then if you are anywhere to the west of it, the sun hasn't gotten to you yet. If you're to the east of it, the sun has already passed your, LAN has already occurred. So we want to know where, when we look up our meridian passage time in the book, are we to the east or west? Are we going to be way before this and miss it if we get out there at 12:06? Or are we going to be 15 minutes early and be out there for too long? So we need to calculate that time difference. Is this making sense so far of why we're doing this? Okay. So how we calculate this time difference is DLO, which means difference of longitude. So that's the difference between two longitudes. You could have a DLO of your departure points, your departure and arrival points. You could have a DLO. It's used as a in a lot of different calculations. Again, our DLO is different than our difference in latitude or distance, because DLO, or difference in longitude, is not equal to nautical miles, because latitude is nautical miles, longitude is not. So we can convert our longitude, our DLO, in arcs of time. And arcs of time are how fast the sun is moving past our longitude lines. So there's a table in the back of our pub that is arc to time. Conversion of arc to time. So go ahead and grab that. Let's see. I'm going to show you on this.
What page are you in the almanac?
I'm on page
I. Yeah.
Yeah. So it's after all of these, but the beginning of the minutes and seconds. So it's kind of grayed out like the minutes and seconds is.
Found it, thanks.
Okay. So you can see 15 degrees is 1 hour because the sun moves at 15 degrees per hour. And that's the basis of this graph. So you can use that 15 miles per hour if you want to do it mathematically on your calculator, but I find it easier to use the table. So look at your table. Let me go back to the PowerPoint so we get what our DLO is. Okay, so the DLO, we are trying to find the difference between my longitudes, the central meridian, I don't even have what it is, but I am 2 degrees and 48.5 minutes west of my central meridian. So I want to calculate this DLO into time. So I'm going to use this time arc conversion of arc to time table. I'm going to find 2 degrees. So from 0 to 59, here's 2 degrees. And my arc to time here is going to be 8 minutes. So I'm going to write in 8 minutes. And then I have the 48 or 48.5. So I'm going to go over to the to kind of the far right column where you get your minutes. You have 0 minutes, and then 0 to 59, and then you have 0.0, 0.5, or 2.5, 5, and 7.5. So our minutes are going down here. We're going to go down to the 48th minute, and then over to 0.5. So we have 3 minutes and 14 seconds. And we're going to put that in, and then we're going to add those up, and we have 11 minutes and 14 seconds. So if my LAN for the sun happened at 12:06, I have a difference of time of 11 minutes and 14 seconds, and that's going to be after. So the sun is going to cross here at 11:06. 11 minutes and 14 seconds later, at 12:17, it's going to pass my meridian of where I am. Okay, how do we follow along on that?
Okay, but you have to you definitely have to know your longitude, obviously, to get that difference.
Yes, yes. So we're going to be using DR. So you're going to want a ballpark of where we are, and then depending on how accurate our DR is, you might give yourself a wider window. So on my LANs, I always go with the earlier time. So sometimes we'll get, you know, a higher second, like 11 minutes and 45 seconds. Technically, that would be closer to 12:18, right? But you don't want to miss it. So you always go to the earlier one. Or just maybe you're not quite sure on your longitude. So just go out there 5 minutes earlier. We could see on our thing, 5 minutes is about somewhere in between 1 degree of longitude. So if we're somewhere within plus or minus 1 degree of longitude, then 5 minutes early would be fine. Okay. Now we're going to do this again. DLO practice, but now we're to the east of our central meridian line. So let's find on our conversion of arc to time table, 3 degrees, 4.5 seconds. How many minutes and seconds difference did you guys get? I'm gonna let you do it before I click over. Any guesses?
So I'm going to say 12 minutes 18.
Yes, 12 minutes, 18 seconds. There we go. So we got a 12-minute and 18-second difference, but this time it's going to happen to us before it happens on that central meridian, right? So we're going to be subtracting. So if it crosses the central meridian at our 12:06, 12 minutes and 18 seconds before that, at about 11:53, it's going to be happening to us. Again, this is closer to 11:54, but you want to err on the side before so you don't miss it. So we have 11:53 is when it would be happening to us.
Now, Bree, this is where I find it interesting that up to this point, it's always been decimals of a minute, but now we're actually into seconds.
Of time,
Yeah.
minutes, seconds.
Oh,
Oh,
that's, yeah.
this is
This
time.
is-
So
versus-
hours, minutes, and
Great.
seconds.
Never- Sorry.
That's okay. Okay. So should we dive into an example? Are you ready? So everyone's got their almanac, right?
Yep.
We have January 2nd, our 12 o'clock DR. So we've calculated our noon DR. What time will LAN occur? And then we will see LAN, and then we're going to get a latitude. So, first we have to calculate what time LAN is. So we go to January 2nd. On our bottom of the right-hand page for daily pages, we see that our meridian passage is going to be at 12:04 for the sun. So that is going to happen on the central time meridian, but we need to use the arc to time to correct for our DR position of where we are. So I multiply 4 times 15, I get 60. So my central meridian is 60, and I'm at 65:38.6. That's my DR. So I have a DLO of 5 degrees, 38.6. With me so far? To the west of my central meridian. So I'm going to use my arc to time. I find my 5. That gives me 20 minutes. And then I go to my minutes side, find 38 point, I'm going to use 0.5. If you use 0.7, you're literally a second difference. So we're ballparking to the minute, so it doesn't really matter. So we have 22 minutes as our difference of time between these two. So if this one happened at 12:04, it's going to be later. So I'm going to be adding that 22 minutes. So I get 12:26 of when my actual LAN will occur for me. Did we follow that one along? Okay. So now it happened, 12:26 happened, and I need to get the two things. I need to get my HS, so I need my sextant altitude, and I need the time of when it actually happened. So again, this 12:26 is based on a DR. So it's based on the DR, but what happened when it actually peaked is going to be when it happened of where I am relative. So it might happen before or after 12:26. So we're gonna need two things to get LAN, the declination and the zenith. Hold on a second. Where do I get my HO? Oh, it was here. Okay, so LAN occurred for me at 12:26:34. I had a Sexton altitude of 54 degrees, 28.1. I had an index error and a height of I. So I need to use this information to get my declination and my zenith distance so I can figure out what my latitude is. So I'm going to plug this information up here into my site reduction form. So I have my GMT, and then I have my declination. So I go, because I was already on my daily pages, I go in for my declination, and I get 22 degrees, 55.2, and then my little d is going to be minus 0.2 because I'm getting less and less on my declination. Then I flip back to the minutes and seconds. I was at 26:34, so I just go to the 26 page. And I had a 0.2 little d, so my correction is 0.1. So I get a declination of 22 degrees, 55.1 south. Again, or never mind, I'm not even gonna go there. Okay. So we have declination, check. Good with that. Now we need to get our zenith distance. Our zenith distance equals 90 minus HO. We have HS. So we need to calculate what our HO is gonna be using our index error, dip, and our A2. So our index error was 1 degree, 10 minutes off the arc. So it's off the arc, we're gonna put it on. So we're gonna be adding that. Our dip correction, we have a height of I of 25 feet. So we go to our dip and we see our correction is gonna be minus 4.9. We can calculate what our HA is. And then we're gonna go to this column over here to find our A2. So we go in with our apparent altitude, HA. So we have 55.33. What do we have? 55. Okay, yeah, 15.6. I feel like my little symbol should be lower. Anyways. So we have a correction of 15.6. We're going to add that, and now we have our HO. So we still don't have our zenith distance yet, but we do have our HO. So now we're going to do 90 minus HO gives me ZD. So I always write it in because it's going to be something. 8960 minus your 55 degrees, 48.8 gives me a ZD of 34 degrees, 11.2. Are you guys with me on how we got ZD? Okay. So now we have our two things. We have declination and we have zenith distance. So we have to figure out, are we going to add or subtract these in order to get my latitude? So I like to draw the picture. Again, we can just look at our latitude. DR is 11. So I'm going to be guessing. We're going to be doing some subtracting, but let's draw the picture. We have a latitude in the northern hemisphere. So if our equator is here, our latitude is to the north. My declination was to the south, so I know the sun is south of the equator. And my zenith distance is from me to the sun. So I'm going to have zenith distance minus my declination gives me my latitude. So I've drawn out the picture, so I have the little formula. and I did zenith distance minus declination gives me 11 degrees, 16.1. Pretty ballpark to where my DR is. So do we think that was a shortcut or not?
Absolutely.
Okay, cool. There's still some work involved, but it is a shorter cut than the full site reduction form. Now we have an LAN. We can use that latitude, excuse me, now we have an LOP. We can use that latitude as an LOP. We're somewhere on that latitude at 1224. Was that it? Or what did this happen? 1226. Okay.
So this eliminates the need for the 229 publication altogether.
Correct.
Nice.
No 229 in any of my things today.
Right.
So that's what kind of makes it the shortcut too. We're eliminating one of the things that we need. All right. Wait, there's more. We're gonna do some more. Are we ready to move on? Or you want to take a little breather? Let's move on. Let's do it. Okay, Polaris. Polaris is the term for the North Star, and it is always less than 1 degree from the celestial North Pole. So for this, we're going to assume it's pointing to the North Pole, give or take a little bit. In order to find the North Star, you want to find the Big Dipper. This is how I find it easily. You find the Big Dipper, and then the 2 stars point, I call them the pointer stars, to the North Star, to Polaris. And then Polaris is also part of the Little Dipper. So when I sit out on my patio, I am facing north. So I can sit out at night and see the Big Dipper and the North Star. So practice that. Practice identifying what the North Star is. It's not going to be the brightest star in the sky. It is bright, but it's not going to be the 100% the brightest, but it will be pointed to from the Big Dipper. So I feel like finding the pointer stars and the Polaris gives me confirmation that I know what star I'm looking at in my head. Has everyone seen? Can everyone find the North Star? Pretty much.
Yeah. I find the handle.
When the marine layer isn't in.
Yeah. I
What was
find
that,
the handle on the Big Dipper is the easiest thing to find.
The handle on the Big Dipper, yeah.
Yeah, and then you can find those 2 other stars on the end.
And then you can find the pointer stars. So I like the pointer stars too. I don't know if anyone has been in the Southern Hemisphere, but the Southern Cross, there's 2 pointer stars that point to the South Pole of the Southern Cross. Like the Southern Cross and the pointer stars points to the south if you were just trying to navigate south or trying to navigate north. Anyways, pointer stars. That's my term, not a technical term. Okay. So we're gonna visualize some of the things we went over in week 1. And I know week 1 was a lot of crazy that I did. So basic terms. We have me, my celestial horizon, and zenith, which is directly above me. On my celestial horizon, I have the north horizon, the south horizon, the east, and the west horizon. So on my horizon, I can have different bearings to different places, right? So instead of talking about the east and the west, which we do a lot, and these are, I'm going to say they're terms. There's the principal circle and the prime circle, but I'm not going to get into that. Okay, so you have the north horizon, we're just gonna call it the north horizon and the south horizon, and zenith. Then we have the celestial equator system, where we have the North Pole, the South Pole, and then the equator. So horizon as our horizon, and then zenith is right above us. The North Pole is directly to the North Pole, and then has the equator. So we're going to combine these two systems to find, let's see. Okay, combining is going to happen in the next slide. Before I move to the next slide, as we're looking at the systems individually, we're going to note that from zenith to the horizon is 90 degrees. From the North Pole to the equator is 90 degrees. So we're going to use that perpendicular relationship between the North Pole and the equator and the north horizon and zenith to our advantage by and how to calculate latitude by Polaris. So say we are looking at Polaris. So zenith is right above me. To the north horizon, I'm calculating because North Star is always going to be pointed north. So I'm going to calculate my HO, right, my altitude of the star. So then if I put on my equator system, if the North Star is here and the equator is perpendicular to the North Star, then from zenith, so right above me, which is where I am, and that equator is going to be equal to the North Pole to the horizon. So our latitude is equal to the altitude of the North Star. So if you are in the southern latitudes and you see the North Star, it's going to be really low on the horizon. If you are at the northern latitudes up in Alaska, that North Star is going to be pretty close to high above you. And that means your altitude of it is going to be very high, meaning your latitude is high. So we have this relationship between, so it's kind of the 90-degree perpendicular, complementary, supplemental, throwing out all these math terms. Okay, this is my, if this North Pole is at the top of the Earth and we are to the south, our, if we're looking at the horizon system, that North Pole is going to be lower on the horizon. Now, if we look at, let me click the, if we are very close, if we're up in the northern latitudes, that North Star is going to be high on the high on our zenith and horizon, and that will make our latitude high because of this 90-degree 180 relationship. Does that make sense? Are you with me so far? Okay, so we're going to go by the rule that latitude of ourselves is equal to the HO of Polaris. So this is another example of it. When we calculate our HO of Polaris, we have a special table. So we're not going to do our typical corrections for Polaris. We're going to use our special table. At the end, okay, let's find, I have it here on page 274, but I don't think that's accurate. No, maybe it is. Okay, yes it is. Find page 274. And this is going to be our Polaris tables. for determining latitude from section altitude and for azimuth. We're not going to go into azimuth in this class, but for latitude, we're going to go into it. Okay. Oops. Okay. So in order to enter the table, we need LHA of Aries. So we don't need LHA of the star or anything else. We need LHA of Aries, and we kind of need the ballpark LHA of Aries. So again, we still have to do a little bit of our site reduction form, but it will be easier. Okay, I want to show you on the bottom of this page, we have the formula, and it's on every page of this table. So the latitude is going to equal apparent latitude corrected for refraction minus 1 degree plus a 0, a 1, and a 2. And if you could see on your tables, we have a 0, a 1, and a 2 for each LHA. Okay, so I have a site reduction form specifically for latitude by Polaris. It's on the Google Classroom. So I have specifically your GMT, and then you only get GHA of Aries, convert it to LHA of Aries, ER latitude, and then your HS to HA is typically what we've been doing. And then our HA to latitude is going to be a little bit different. So we can go with our steps. Do I have another picture? Yes. So our step 1 is to observe Polaris. So to observe Polaris, you need 2 things. You need the horizon and you need the star in order to see it in the sextant. So you can get Polaris, you know, at sunrise or sunset, twilight, but sometimes if you have a full moon and you have a clear horizon and that full moon isn't dulling Polaris, so you could still identify where Polaris is, you can shoot this latitude at any time of the night if you have that clear horizon. So you need a clear horizon and you need Polaris. So to observe, to get an HS of Polaris. So we're going to observe Polaris with HS and note the time. Then we're going to use that time and get LHA of Aries. So we do our GHA, minutes and seconds, longitude to get LHA of Aries for that specific time. And then we are going to convert our HS to HO using the special table. So in this case, I have it as HA, you have all the corrections, and it equals your latitude because HO is equal to latitude. And that's our LOP. Okay, what do all these corrections mean? Our A0, we go in with our LHA of Aries. So that's the distance between Polaris and the pole. So again, it varies slightly, right, within that 1 degree. So depending on the time of the year, I guess, it's going to be a little bit different within plus or minus 1 degree. Then we have our A1 correction, and that is based on our latitude. So A1 here, we go in with our latitude. So that corrects for the angle of view of the diurnal circle, which varies depending on the observer's latitude. A2 is the correction for variations in SHA and the declination of Polaris, which varies with date. So again, very, very small corrections, these or differences between each of these. So if you were, you know, I don't know, this one here, we have January, February, March, it's all the same correction. So again, you go by the month that you're in, but it's generally what you're going with. Okay, so let's do an example. Are you guys ready? Should we dive right into this? Okay. Okay, so we have October 15th, 2020. We're shooting evening stars and we measure the altitude of Polaris. We have a 1800 DR, and these are our notes from our Polaris site. The time was 1817, HS, index error, height of eye, what is your latitude? So again, these are the things that we're going to need for every site. Basically, your HS and the time, your IE, and the height of eye. Okay, so first I plug in the information that I know. So this all just came from the problem, the navigator's information, if you will. I did have to calculate there my GMT. So I had zone time, DMT, or zone description, GMT. With my GMT time, I'm going to calculate my Aries. So I have 55 degrees just for the top of the hour. And then I go to the minutes and seconds page. And under Aries, remember, we don't want to go under the sun and planets one. We're only doing Aries. We get our minutes and seconds correction. So we add that up. And then we're going to put in our longitude. And I'm this kind of going fast. We're going to get in our longitude. So we get our LHA, and then we have our DR lat. Okay, let me see where are you guys doing the problem with me or kind of following along?
Following.
Am I going too fast?
Just following. Yeah, I couldn't flip the pages fast enough to.
We can't write that fast.
Yeah. But we've all done this before, or we've all done these steps before. So I feel like we know how to do this so far. But we are going to be doing examples. We are going to do practice. Okay. So we calculated our LHA varies. We're all pros at that now. And then we have our DR latitude. So for HS, we need to calculate our index error. Our index error was off the arc, so we have to put it on, meaning we're going to add. And then our dip, we all know how to get dip now with our height of eye, and we always subtract dip. So we have our HA. So now we can go into our Polaris tables. So let's look at our Polaris tables. This is what I wanted to see. Okay, so we had an LHA of 295, 10 minutes. So for LHA, we have to find the section where we would see 295. So we're at 290 to 299. So that is going to be, for me, on page 276. So we're in that column. So we're going to be in that column the whole time. So I might, put something next to it. So I know I'm going to be somewhere in that column. And then for my LHA, it was 295. So I'm going to go with my 5 degrees. If I'm closer to 296, like I'm 295, 45 or something, then I would go with the 6. And there are kind of a little bit of differences here. So you can mentally interpolate if you want. Again, this is going to just make just a slight little change. So just up to you of how much you want to interpolate. So we have our, following our HO, we always subtract 1 degree, and then we have our H0, we have 1 degree, 12 minutes. And then moving down, so we're in that same column, and we're going to go in with our latitude. Our latitude was 38, 18. So we're going to go in at 40. So we're closest to 40 at 38.18. Again, if you were at 30, it was 0.5. If you were at 40, it was 0.5. So your 38.18 is still 0.5. So same column, we're going to work our way down to A1 or A2, excuse me. And the month that we took this site was October. So same column, we find October and we get 0.9. So now we have our we add our A0, A1, A2, following that same column. We didn't deviate from that column. And we add up all those numbers, and we get our latitude. It's ballpark close to our DR latitude. So are we going to call this one a shortcut? What do you think?
Yeah.
We still didn't have to use Pub 229. We did have a new table, but it's generally speaking a shortcut. Okay.
But from a practical standpoint, you can't really use it like the sun and do a couple of different sites throughout the day, right? The only thing you can get from this is just a line of position.
Correct. Correct. It's not moving. So it's just if you're shooting other stars or something and you see Polaris, you can add that, adds in a line of position. So if you had 3 stars, but 2 of them turned out bad and you couldn't get a good line of position, you got 1 good star and a lat by Polaris, you still have 2 lines of positions, which would be a better fix than just a DR or 1 line of position.
Got it.
So yes, you don't really shoot it throughout the day. If you're really changing altitude and it's a full moon and you can see it, in the evenings, the sun's not out, right, for half the day, depending on where you are, that you can, if you're in the northern latitudes and it's dark, whatever, 20 hours a day or something, then you might be shooting Polaris to check your latitude. But again, you won't have that bearing change like you do for the sun, because Polaris is always north. So you won't get a change in your LOP bearings. You like to have them spread. Anyway.
Would it be practical to do 1 in the morning and 1 in the evening? Or is that too big of a difference?
No, you could. I would say if you are headed east or west, generally speaking, then you're not going to get a big difference there. But if you have a change in latitude, then you can DR those and you can get across, make it a running fix.
Got it.
But if you're not changing latitudes, your 2 latitude lines are going to be so close.
Got it.
Okay. Wait, there's more. Are we ready for a little bit more? Any big questions on latitude by Polaris? So those were our two shortcuts.
Sorry, just that
Latitude
1
by
degree.
LAN.
Sorry
And
about that.
what was that, James?
Yeah, just the 1 degree. That was just the difference between Polaris and North, right? On the calculation form, the -1 degree.
I'm going to say no. If you look at it,
Right below HO.
yes. So it's apparent altitude -1 degree. And how I was saying that LHA, this first table, LHA of Aries, kind of corrects for where the North Pole is into relationship to the celestial North Pole. So you can see on the higher LHAs, you do have that 1 degree, but on the lower LHAs, you don't have. So if you change to page like 274,
Mm-hmm.
you don't have that 1 degree. So you would be subtracting a degree.
Okay.
So it kind of just takes into account of where it is in this table of calculations.
Yep, got it. Sorry, I just missed that. Yeah, thanks.
Yeah. Okay. Okay, now we're gonna do a quick little twilight, and then we're gonna do some practice problems. Okay. There we go. So when do we shoot the stars? In our daily pages, we have nautical twilight, civil twilight, and sunrise or sunset. So when does all of this happen, and what does that mean? It's where the sun is in relationship to the horizon. So sunset is when the sun passes the horizon. Civil is going to be when it's between the horizon and 6 degrees below the horizon. Nautical twilight is going to be 12 degrees. So it goes 6, 12, 18. So your civil twilight will be the brightest. So that's when you're first going to start seeing stars. So whether, if it's sunset, you're not going to see any stars, right? It's all daylight. And then when the sun starts setting, it's going to pass sunset. The sun is going to set. And during the civil twilight, we're going to start seeing stars. And then nautical twilight, it's a little bit darker. The sun is more past the horizon. And we're going to see more stars. And then you get astronomical. But as the sun gets lower and lower, that horizon gets harder to see. So we always need those two things. We need the celestial body and the horizon, and we need both of those clear, not covered with clouds on the horizon, not covered with clouds on the star, in order to get those to a solid sight on your sextant. So if you're getting morning stars, you're going to want to start your shooting at the earliest possible time, which would be your nautical twilight. So you're going to be able to see all the stars, but you can't see the horizon because it's so dark. But as that sun gets closer to the horizon, you'll start to get a clear horizon line, and that's typically your nautical twilight. And so you'll start be able to see the stars and the horizon, and you could start shooting until you get to civil twilight. You'll be able to see most of the stars, again with the bigger magnitudes, because now you have more light filter. And then once the sun comes up, you can't see as many stars, but you'll have a solid horizon. Again, kind of opposite when the sun's going down. You'll have the horizon, but you won't have the stars, and then you'll start to see the horizon. With this also works when you're planning out which stars you're going to shoot and which stars you're going to shoot first. In the morning, you're going to see the stars, right, everywhere, and then you're going to see the horizon first in the east, because the sun is rising in the east. So you get to shoot those easterly stars, or generally in the east, first, into like probably in the nautical twilight, and then in the civil twilight, where you have a clearer horizon and you still have the stars, that might be in the western. So when you're planning which stars to shoot, if you're just looking in the west, finally get that star, and then you have no horizon or no stars in the east to look at. So that goes with planning about where the horizon and the stars are all going to be. So when we are planning, we want to know when these times are going to be. So for morning stars, when is nautical twilight and for evening stars, when again is nautical twilight, when we're not going to be able to see a horizon afterwards. Does that make sense on what those terms mean? Okay. So how do we do this? We look at our table, our I'm gonna bring it up here. Okay. So we have our nautical twilight and our civil twilight and then our sunrise. So if we are at 30 degrees north, ballpark, in September, just because I have it on this page for some reason, our nautical twilight is at 4:50, and then it gets to 5:18, and then it gets to actual sunrise. So again, the sun is rising and it goes through that 12 and then 6 and then past the horizon. So I'll be able to start shooting at about 6:40, or excuse me, totally messed that up, at about 4:50. So I need to calculate, I need to apply 2 corrections because this number is for 30 degrees north. I'm not at exactly 30 degrees north. And then it's also at my central meridian. I am probably not at my central meridian. I'm east or west, just like we did for that LAN. I'm east or west, and you have to do the DLO, arc to time conversion. So our first step is to correct for latitude. So our latitude is like 33 degrees something, I don't know. So I know I'm between 30 and 35. So I like to write at 30, it was 0450, and at 35, it was 0444. So this is kind of that interpolation. I'm just going to call it 30. I don't know what latitude we're at. So what is my latitude correction? So we go back to the table, we go back to the almanac, and we're going to flip to the very back, past the minutes and seconds, and we're going to get to a page that says table for interpolating sunrise, moonrise, etc. for latitude. So mine is XXXII. So in case we forget, it does give us a great description here. Okay, so we have a couple different things here. Our first thing is here is called tabular interval. So that means what is the difference? Oops. Again, I don't have my page number anymore, but this, in case this one starts at 0 and it has a tabular difference of 10, 10, 10, and then it goes 5, 5, 5, and then 2, 2, 2, 2, 2, 2. So the lower latitudes have an interval of 10, mid latitudes interval of 5, and higher latitudes interval of 2. So when we go back to this page, we have a tabular difference of 10, 5, or 2. In my case, it's 5, right? 5 tabular difference. So we are going to be in this column for 5. So now I want to know what is my tabular difference. And we're always going to go from the bottom. Let me make sure I get that right. I'm pretty sure that's right. Okay. Oops. Pretty sure we're always going to go from the lower latitude. So in my case, I'm at 3 degrees, 30 minutes. So on this page, I'm going to find 3 degrees, 30 minutes. So I'm going to be somewhere along this line. Now here, I go in with the differences between the consecutive times. So back to this one, I had, this was 44 and 50. So my difference between these 2 times would be 6. Go back to this one, and I'm real close to the 3, or the 5 minutes. So excuse me, I got ahead of myself. Real close to the 5 minutes, so I'm going to use 3. So my time is going to be 3 minutes, and I have to decide if I'm adding or subtracting. This is 350, and this is 444. I'm going to go with 447. This will look a lot cleaner when we do an actual example and not one that I just made up on the spot. So this 447 is the time on my latitude line that it passes the central meridian. But now I have to correct, am I to the east or west of that central meridian? So we do our arc to time. Go back. So we do our DLO arc to time correction for longitude. So we have the latitude table for latitude, and then the longitude will do DLO arc to time. And that's finally it. That's our new information for today. How you guys feeling?